In today's statistics lesson, we will be discussing confidence intervals for the mean where the standard deviation of the population is known. Please feel free to press pause and read through today's objectives. All right, in order to create a confidence interval for the mean, we first need to talk about the mean. So the mean of our population is given by mu, and our sample statistic, so our sample mean, is given by x bar. X bar is what we call an unbiased point estimate, because what that means is if we take a bunch of samples, all the same size of the population, and we calculate the x bar, that x bar will cluster around mu. It'll be very, very close to it. So we call that an unbiased point estimate. All right, so let's start by calculating some of those unbiased point estimates. So in this problem, we have a research that has collected data about college athletic conference and its student athletes. So it sampled 40 student athletes and asked them the number of hours they spent on their required athletic activities for 1 week. So that is given in that small chart right there on the left. All right, find a point estimate for the population mean, mu, which is the mean number of hours spent. So again, we are just calculating x bar. And if you remember, this is the same way that we calculated x bar in earlier lessons, right? We add up all the points and then we divide by the number of points that we have. So in this case, we would add up all those numbers, and that total turns out to be 797, and our n is 40, so we would divide those. And this one you will have to round, since our data is has no decimal points, we will round to 1 decimal point, so 1 more than the given data. So the mean for the sample is 19.9 hours. So that is our point estimate for the mean number of hours spent, 19.9. All right, and then what we're going to do is we're going to take this point estimate, we're going to build around it. And that's what we're going to do. We're going to do an interval estimate to create some level of confidence around that point estimate to say, hey, we're pretty sure that this is where our real population mu lies. So that interval is going to be used to estimate that population parameter mu. And we're going to, in order to do that, we're going to have some kind of margin of error around that x bar. And it depends on how confident we are about that estimate, how confident we are that that estimate actually contains the mu. So that's the thing we really need to work on, is our level of confidence. All right, so some textbooks call this C, every textbook might call it something different. So just make sure that you pay attention to whatever your textbook says. So what the level of confidence is it's just the probability that the interval that we create contains that actual population parameter. So the level of confidence is just 1 minus alpha. Alpha is what we call the significance level. We will be talking more about alpha later, because that also turns out to be the probability of an error happening when we do hypothesis testing. So we'll talk about alpha later. So for example, if you have a problem that says alpha is 0.10, that's 10%, then that means the level of confidence is 0.90 or 90%. And vice versa. If you know that the confidence level is 90%, then you also know that the alpha is 0.10. So you can use those two together. They are basically complements of each other, the level of confidence and the significance level. All right, so we're going to use that alpha from the level of confidence to find what we call critical values. All right, and critical values are what separate your sample statistics that are probable from statistics that we might find that are highly improbable or unusual. So in this picture, I have broken down how you would look at that. So if you have a 90% confidence level, that would mean that this would be, the area of the blue would be 0.90. That means we have 10% of our data left over, and that would give us 5% up on the high end and 0.05% on the low end. So those two 5% together make up that 10%, which is alpha. But notice I had to break it in half because I had the high end unusual values that might occur and the low end unusual values that might occur. once we have that, we can calculate the critical values, and these z's right here, those boundaries that separate the probable from the improbable, those are what we call the critical values. And we can find those because we know we can find the one on the lower end especially easily, because we know that we can find the area here, which is 0.05. We can go to our tables and we can find the z-score that corresponds to an area of 0.05, and it turns out that that is negative 1.45. So that would be the negative end. On the low end is negative 6.45, and then the high end would be the positive, because again we are dealing with a normal distribution, so everything is symmetric. The most common ones are listed up here at the top. These are the ones that you're going to see the most often: 90%, 95%, and 99%. So I highly recommend that you just memorize these rather than having to look them up every single time, because you will see them quite a lot. If we were going to do the 95% confidence level, then that would mean the area in blue in the middle is 95.95. The area of each of these wings would be 2.5%, right? 0.025. And then knowing that this area is 0.025, we could look that up on our chart, on our table, which would give us that. And there we know the high end as well. So those are our corresponding z-scores. Sometimes you will see them referred to as z sub alpha over 2, because they're taking that alpha, they're cutting it in half, and then finding the z-score that corresponds to that. So the z sub alpha, the z sub 0.025 corresponds to negative 1.96. And then you would also know that the positive side would be 1.96. So feel free to memorize those few values because they do come in handy, but just know that you can always go back and find them on your chart. Sometimes they're going to ask you to find critical values and levels of confidence that aren't one of those three. So we're going to go through a couple of examples of those on how to build that. All right, so find the critical values for an 84% level of confidence. So here's my picture, and I'm a big fan of drawing the picture so I know what everything looks like. That means inside here, I want this area to be 0.84, which means my alpha for this case would be 16, right? Because my alpha would just be 1 minus 0.84, which would be 0.16. So that means I have this area up here is 0.08, and this area down here is also 0.08. So I'm going to use this one down here to find the critical value down here on the low end, because that's definitely easier to look up on my z-score chart. So I go to my table and I find an area of 0.08, and then I look for the z-score that corresponds to that. And there isn't one that is exactly 0.08, but the closest one is negative 1.41, which means that this high one, this critical value over here, is 1.41. So if you want to write that using the z, so the z of alpha over 2 would be z of 0.08, and that turns out to be your 1.41. And some textbooks will put a plus or minus in front of that, and some won't. Some will just ask for the positive side. It just depends on the textbook that you're using. Personally, I just want the positive one, but if you put a plus or minus there, I would not be upset at that. All right, so if you would like to, you can press pause and try this one on your own. All right, so how would we find the critical values for a 97% confidence level? So when I draw my picture, right, I want 97% in the middle. So this area would be 0.97. That means my alpha would be 1 minus 0.97, which would be 0.03. So that means I would have 0.015, so 1.5% in the upper side and 1.5% down on this lower end. And then again, I would use my table, look up that 0.015. And I don't have one that is, I do have it exactly, 0.0150. So that would be a critical value of negative 2.17. So this critical value up here would be positive 2.17. So again, if you were going to write it as your z of alpha over 2, that would be z of 0.015, and that is 2.17. Again, some books might put the plus or the minus, but I'm looking for that positive one. That's really all I need. All right, so that's how you find those critical values by hand if you need to. But usually 90, 95, and 99 are the most popular. So those are the ones we will see the most often. All right, sampling error. Anytime you're taking samples, there's going to be some error. So the sampling error is just the difference between the X bar and the mu. Right, so the difference between our sample statistic versus our population parameter. The mu itself is generally unknown. We may know it though, they might even tell us what it is. And X bar varies from sample to sample. So that sampling error, and I'm sure you've seen sampling error like on television when they talk about polling, they'll be like, the margin of error is 3%, right? That's what they're telling you. The sampling error is 3% either way, either positively or negatively. So we're going to walk through the process on how to find that margin of error. All right, so the margin of error is sometimes called the maximum error of estimate or error tolerance. Again, it depends what books you use, what name it will be called. But what it is the greatest possible distance between your point estimate and the value of the parameter that you are estimating. It is denoted by capital E, and this is the formula. You will take that Z critical value for your level of confidence, multiply it by sigma, and again, this is only when we actually know what sigma is. If we don't know what sigma is, there's something different that we need to do, and we'll talk about that in the next lesson. And then divide that by the square root of n. So that is how we find our error. Make sure that your sample is random and make sure that you have a population of greater than 30, or it tells you that the population is normally distributed before you can use this. So if we look back at that data from example 1 about the student athletes where the mean was 19.9, and we're going to take a 95% confidence level to find the margin of error for the mean number of hours spent on required athletic activities by all these student athletes in the conference. Okay, and it says assume the population standard deviation is 2.4. So I'm going to write down all the information that this problem gave me. The first thing I know is it gave me the sigma, right? My sigma was 2.4. The mean I calculated earlier. Oh, whoops, nuts. I calculated the X bar earlier, right? That was 19.9. Okay, and we want a 95% confidence level. So that means my alpha is 0.05. Okay, so all these things you can write down. The C is 0.95. Write down all the information that you can get from this problem. But what it wants you to find is find the margin of error. Okay, so if you're finding the margin of error, the first thing you should do is write down the formula for the margin of error. So let's start there. So the margin of error equals the critical score, the critical value for that confidence interval, times sigma divided by the square root of n. And n is 40, and that we got from the example 1 as well. Okay, so we need to use the critical value for 95%. So if you have a 95% confidence, that's one of the ones you should memorize because you're going to see that one often. That is 1.96. And again, if you needed to find it, you could do it the old-fashioned way and draw the picture and do all that like we did in the previous example. You're going to multiply that by your sigma and then divide by the square root of n. And then you're just going to throw all that in your calculator, and you are going to round that, and that turns out to be about 0.7. So that means that our margin of error is about 0.7 hours. So we're 95% confident that the margin of error for this is 0.7 hours from that mean of 19.9. All right, so that's how you would calculate your margin of error. Just use this formula, plug in the information, and make sure you have a label. A lot of people forget to label theirs, so make sure you have a label. Margin of errors you see a lot in polling. So I wanted to show you some examples that I pulled offline. So we are using some fictitious election results that I found on Pew Research, and again, these are all made up. On how the margin of error is affecting both races that are presented. So this is just a discussion problem, and we're just going to take a look at these races. So let's look at race A. All right, so it says the margin of error for a single candidate is plus or minus 3 percentage points. So if you look, the means are given, right? So they did the polling, 48% said Republican, 43% said Democrat, but they had to calculate their margin of error, which was 3 percentage points. And that's what these little whiskers on each end represent. And notice here that the whiskers are overlapping. So because the whiskers are overlapping, that means that there is a statistical tie here, because given that margin of error, they could be polling at exactly the same percentage. There's not really, the Republican candidate really isn't 5 ahead because there's overlap here. Notice in poll B, we have no overlap. So that means the Republican candidate truly is ahead because there is no overlap, even including that error that is possible. So you definitely want to pay really close attention to the margin of error that they give you on the news, because they often just tell you these numbers, the 48 and the 43, and you say, oh, they're ahead by 5, so the Republican candidate's going to win. Well, when you include the margin of error, it turns out that's not the case. They are statistically in a dead heat. So make sure you pay attention to those. Over here in race B, the margin of error for the difference between the candidates. So if we look at the complete difference between the two, it could be as high as positive 11 in poll A, right? If we take the very top of here and subtract it from the very bottom here, it could be as high as 11, or it could be -1. And that's what tells you, because 0 is included in this, that means that they are in a statistical tie. But if you take the highest point here and the lowest point here and you subtract them, notice you're no longer on that 0. At most, they're 14 apart, and at the smallest, they're 2 apart. But they are, as you can see, above 0. So this one clearly shows that the Republican candidate's winning, and this one shows that they are in a statistical dead heat. So make sure you really pay close attention to the fine print, because a lot of the times, especially news outlets, won't be very forthcoming with that information. They'll put the margin of error in really small print at the bottom. So make sure you actually pay attention to that stuff. All right, so how do I create a confidence interval for my population mean? All I have to do is take my sample mean and just add or subtract the error to get the low end and the high end. And you can see it written different ways. Some people will just write it as x bar plus or minus e. That's a different way that you could write it. You could also write it in interval notation, where the low end is x bar minus e and the high end is x bar plus e. Most people leave it in inequality notation, but again, all three of these are equally legitimate ways to answer this question, and you will see it written differently depending on who is writing the article or the topic or the textbook that you're reading. But in general, here are the steps that we need to construct a confidence interval. All right, so I'll let you press pause and read through these 5 steps. All right, we are now going to use those 5 steps to find our confidence interval. So we're going to still go back to that data from example 1, using that margin of error that we calculated for that example, and we're going to construct a 95% confidence interval. Okay, so what we're going to do is we are going to take, well, first of all, we need to know to construct our confidence interval, we need to know x bar and we need to know the error, because we will take the x bar and add the error, and we will take the x bar and subtract the error to get the high end and the low end. So the x bar that we found was 19.9, so both of those will be 19.9. And the error we found in the other example was 0.7. So I will subtract it from the low end and I will add it to the high end. And that will give me 19.2 in the low end and 20.6 hours on the high end. So what that means is I'm 95, so I'm going to write this in words. I'm 95% confident that the population mean is between 19.2 and 20.6 hours. Okay, so the more confident you are, the better off you are. So if you could create a 99% confidence level, that would be even better. So let's go to that and see what happens when we do a 99% confidence level. All right, so same issue, but this time we need to calculate the new error because we have a different level of confidence. Okay, so our x bar is still 19.9, but we need to calculate that new margin of error. All right, so if you remember from before, the 99 was one of the ones I asked you to memorize, and that was 2.575. So those are your critical values for 99%. Okay, we're going to calculate the error. We're going to start with our formula, and we're going to plug everything in. So the critical value is 2.575. We're going to multiply that by the sigma. And if you remember from before, the sigma they gave to us, which was 2.4. So 2.4, and then divided by the square root of 40 because the n was 40. And then we put all that in our calculator, and I get approximately 0.98. So 0.98 hours is my margin of error for this. So my x bar minus my error and my x bar plus my error. So 19.9 minus that 0.98 is going to be less than mu, which is going to be less than 19.9 plus 0.98. All right, so that would be, if I subtract these two, I get 18.92. And if I add these two, I get 20.88. So I am 99% confident that the population mean of the number hours of spent on the required athletic activities in a week is between 18.9 and 20.9 hours, if I round to the 10th place. And they will tell you how many places you should go. I usually go one more than the data itself, and the original data was all in whole hours. So I would round that to 18.9. And this one would be to 20.9. And again, you can write that a bunch of different ways. If you wrote it in interval notation, it would be the interval from 18.9 comma to 20.9. So again, it just depends if you use inequality notation or you write it in interval notation, but it's the same answer either way. All right, so if you want to try one for yourself, go ahead and press pause here and then try this one. All right, so the first thing I'm going to do is I'm going to read the problem and pull out all the important information. A college admissions director wishes to estimate the mean of age of all students currently enrolled in a random sample of 20 students, so n equals 20. The mean age, so in that sample, so that's my x bar, they found the average to be 22.9. From past studies, the standard deviation is known, so the standard deviation of the population is 1.5. And the population is normally distributed. Good. So we don't have to worry about the fact that our n was smaller than 30 because they told us the population was normally distributed. They want us to construct a 90% confidence interval. So my C is 0.190. And again, that was one of the ones I asked you to memorize. So that Z critical score that goes with 90% is going to be 1.645. So again, if you don't know, if you didn't have that memorized, then you'd have to go back and calculate it like we did with the other problems. All right, so let's find our error, which is our critical value times sigma divided by the square root of n. So 1.645, and then we're going to multiply that by 1.5 and then divide by the square root of 20. So I put all that in my calculator, and I get that to be about 0.6 years. So there's my error. So the low end of my population estimate would be 22.9 minus that 0.6. And the high end would be 22.9 plus that 0.6. So my low end is 22.3 and my high end is 23.5. So I am 90% confident that the mean age of all the students is between 22.3 and 23.5 years old. So that's how confidence intervals work. Pretty straightforward. All right. When people interpret these results, there's some problems that could occur. And a lot of newscasters get this stuff wrong. Okay, so it's incorrect to say there's a 90% probability that the actual mean is between 22.3 and 23.5. That is incorrect. Don't say it that way. So you can say it, if a large number of samples is collected and the confidence interval is created for such a sample, approximately 90% of the intervals will contain mu. That one kind of confuses people sometimes, so I like to go with the last one. I think that's the most correct way to say this. I am 90% confident that the true mean of the population lies within the interval 22.3 to 23.5 years. The one in the middle can be a little confusing, so I want to talk about that one. So what it means is if I took a bunch of samples, so each of these dots represents a sample mean, and that dotted line represents the actual mean, the population mean. Notice that all of these bars cross with their margins of errors. That's what those whiskers represent, those margins of errors. 1 out of the 10 didn't make it and didn't cover that mu. So that's what it means by 90%, that when we take a bunch of samples, 90% of those samples would contain that mu, so 10% of them might be off like this where they wouldn't cross. But I think a lot of people sometimes find that confusing, so I really like to use that last. That last one I think is the most succinct way to say it as well. So I'm a big fan of short and sweet and to the point. All right, another thing that we can do with these confidence intervals is find the sample size that we need. So there's oftentimes, if you want to go back and recreate a study, you will need to know how many people you need to go and take a survey of. So that this also comes in handy. So what they did is they actually just took that margin of error formula and feng shuied it. So this is exactly the same formula, just rearranged. They have solved for n instead of solving for e. So you can use that to find your margin of error that you need. So you need to know the critical score for your level of confidence, your standard deviation for the population, and your margin of error that you want. Take all of those, multiply those two, divide by e, and then whatever you get, square it, and that will tell you n. N often does not come out to be a whole number. Oh, that should say whole number. I'll make sure I fix that. It's not a whole number. Then round it up to the next whole number. If your sigma is unknown, you can estimate it using S, but you have to make sure that you have at least 30 members. If not, then I will show you something different here in the next lesson on how to do that. So we're going to go through a couple of examples where we have to find the sample size we need to recreate some data. So, for example, if I was a researcher in example 1, and I wanted to estimate the mean number of hours spent, okay, how many student athletes must be included in the sample for 95% confidence level to be there? And we want the margin of error to be 0.5 hours. So this is my E. This is my level of confidence, right? So that will help me find my Z. So my C is 0.95. And from that, I can find my critical value, which that's one of the ones I asked you to memorize. That was 1.96. And we know that the sigma from before was 2.4. So we have all the important information that we need. And my E is 0.5. So I'm going to write down my formula. So N equals, it's the critical score, critical value times sigma divided by E squared. All right, so that would be 1.96. I would multiply by sigma, which is 2.4. I would divide by 0.5, and then whatever all that is, I'll square it, and that'll give me N. And that turns out to be 88.51. And since I can't have 0.51 as an athlete, I have to round it up. So that would be 89 athletes I would need to go talk to and get their information to be sure that I'm 95% confident. So it's a nice way to be able to find the minimum sample. Again, you can take more, but that's the minimum that you can get. So if you survey less than 89, then your results wouldn't be valid. All right, so here is another example if you would like to give it a try. All right, so let's write down all the information we need. All right, so we're filling half-gallon bottles. The company wants to estimate the mean volume of the water, putting the, okay, within, there we go, there is our margin of error. So our E is 0.25. Our confidence level is 95%, which means my Z, my critical value would be 1.96. Determine the minimum sample size which was required to construct that 95% confidence level. Assume the population standard deviation is 1 fluid ounce. So my standard deviation is 1. All right, so I'm going to write down my formula. I'm going to plug everything in. So 1.96 times my sigma divided by my error, which is 0.25, and then square everything. And that turns out to be 61.4656. So I would need to sample 62 bottles. right? And it doesn't matter that this, and a lot of people say, wouldn't you round it down to 61? No, I need that 0.46 of a bottle, so that means I need a whole nother bottle. So make sure you're always rounding up, no matter what that decimal is. So 62 bottles. All right, so please make sure you come back next time when we talk about how to do all of this if we don't know the standard deviation of the population. So we're going to go through all the same stuff, but do things a little bit differently. So hopefully we'll see you next time.